Hello and welcome back. In the previous lectures, we dealt with calculation of the change in thermodynamic properties which have a single component, one chemical species, or in fact those calculations we have done will also be applicable for systems where the composition is constant, even if it is a mixture. As long as the composition is constant, all the equations we have dealt with are applicable. So what we will do in this lecture from now on is try to deal with the mixture of chemical species, because that is most commonly encountered in a chemical process industry. When we have a mixture of chemical species, the behavior of such a mixture is going to be different from the pure component counterparts. Right? When we mix, there are going to be other types of interactions that take place in the mixture between the two distinct chemical species, and somehow we need to account for these type of changes, or at least know how to formulate a thermodynamic framework to handle a mixture of chemical species. And we do that. One of the ways we do that is through what is known as a solution thermodynamics approach. We need to define additional thermodynamic properties than what we have done so far to be able to lay the theoretical framework for dealing with mixtures. That is what we'll try to do in today's lecture. We start with a simple example. If you recall, the one we discussed in one of the introductory lectures. Let us say I have a mixture of methanol and water. This is methanol. Let's say I have 0.3 moles of methanol, and the molar volume for methanol is about 40.7 cc per mole at room temperature and atmospheric pressure. And then I have another beaker which contains water, and I have about 0.7 moles of water, and the molar volume for water at the same conditions is about 18.1 cc per mole. Because I have 0.3 moles, this total volume for one here is about 12.21 cc, and the total volume for the water I'm taking is about 12.67 cc. This is number of moles multiplied with the molar volume. Now once I have these two distinct chemical species and I try to mix them, the resultant would be a mixture of these two compounds, right? And if I pose a question, what would be the total volume for this mixture, then we would be tempted to say that it's going to be 12.21 plus 12.67, which is 24.88 cc. However, it turns out when you do this exercise, the volume you measure is not 24.88 cc, rather it is 24.03 cc's, lower than what you would expect by a simple additive rule, mixing rule you apply for this particular scenario. That's because the interactions between methanol and water are going to play a role in determining the molar volume for this particular mixture. So then it turns out, if I have a mixture, I cannot simply use the information on the pure components and try to tell what the molar volume for a mixture is. In fact, it is true not just for molar volume, but for any thermodynamic property, be it enthalpy, be it entropy, or Gibbs free energy. The mixture is going to behave differently than the pure component counterparts, or by simple addition of the pure component properties. Now, let's also take this discussion a little forward so that we can define a new thermodynamic property. Let us say I have 1 mole of this mixture, as we have seen here, and this 1 mole is going to occupy 24.03 cc, and this particular value, let us call this as the volume of the mixture. This is the total volume of the mixture. The total number of moles, we will drop the subscript. N1 is for methanol, N2 is for water, N is simply N1 plus N2, which is 1 mole. So the molar volume, or the total volume in this case, because I have 1 mole, is going to be 24.03 cc, or cc per mole. And then the mole fraction in this scenario, let's write the mole fraction for methanol with this subscript 1 in this scenario is 0.3. So now I have a case where I have a mixture with 0.3 mole fraction for methanol, whose total volume, or the volume occupied by 1 mole of this particular mixture, is 24.03 cc. Now, if I take this mixture and I decide to add a little bit more methanol to this mixture, let's say I want to add some additional number of moles of methanol to this mixture, a small quantity, 0.001 moles. Now this additional number of moles is going to contribute to additional volume, right? And that will increase the total volume of the mixture, right? So it turns out V total, when I add this additional number of moles, this V total would go from 24.03 N equal, the total mixture is N equal to 1 mole, X1 is 0.3, to 24.0686 cc's. N is 1 plus 0.001 moles of methanol. So this particular quantity here is delta N1. We have added pure methanol to this mixture, and the mole fraction has changed from 24.03 to 24.0686. Just as in case of adding methanol and water, a pure additive volume is not going to work. Even when I add the additional number of moles, the difference is not going to be directly related to 0.00 or the volume of 0.001 moles of methanol. So if you look at it, delta V is, in this scenario, delta V total is, in this scenario, 24.0686 minus 24.03, which is 0.0386 cc's, right? And I have added 0.001 moles. So if I divide this, the change in the total volume with delta N1, 0.0386 over 0.001, if I divide the total number of moles I've added, or the total volume change with the total number of moles I have added for methanol, this value turns out to be 38.6 cc per mole. And note that this value is not equal to V1, the molar volume of methanol. Molar volume for methanol is right here, 40.7 cc, whereas when I divide the volume change with the number of moles I have added, what I get is 38.6 cc. So this number is different from 40.7 cc, as you would expect once we looked at the first scenario, that when I add, they don't simply, the volume simply don't add up. So when I add additional number of moles, the volume change is not going to be directly proportional to the molar volume of methanol. So this is an important observation. This change, limit of delta N1 going to 0, delta V total over delta N1 is not equal to V1 in this scenario. So we will give this particular limit a name. We will call it as V1 over bar, and we call it as partial molar volume. We'll come back to why that name has been used for this particular case when we derive more relations. But for now, let's call it as partial molar volume. It is the change in total volume of the mixture divided by the change in additional number of moles I have added for methanol. In this case, I have added methanol So the subscript for partial molar volume will be for methanol, which is 1, right? Similarly, if I take limit of delta N2 going to 0, the change in the total volume of the mixture over delta N2, this will not be equal to the molar volume of water, but rather it would equal what we call as V2 over bar. This is still partial molar volume, but in this case it is partial molar volume for water. In the previous case, it was partial molar volume for methanol, right? So we have a scenario where the mixture behaves differently, right, than their pure component counterparts, and V1 bar is not equal to V1, at least in this case. In certain cases, they may be equal, but they don't have to be. And V2 bar is not equal to V2. The partial molar volume for methanol is not same as the molar volume for methanol. The partial molar volume for water is not same as the molar volume for water. So we have defined a new property for a mixture, partial molar volume, right? In fact, we can mathematically write this limit as the derivative of the total volume of the mixture, which is the number of moles multiplied with the molar volume of the mixture, N times V, over N1, the derivative of this quantity. Remember, we have taken that example at constant pressure and temperature, room temperature, atmospheric pressure, we said. And when we change the number of moles for methanol, we are holding the number of moles for water constant, N2. This quantity is called as the partial molar volume. This quantity is what the limit represents. So mathematically, we're going to define V1 bar as the partial derivative of the total volume with respect to the number of moles of methanol when we hold the temperature, pressure, and number of moles for water constant. Similarly, if I need to define the partial molar volume for water, it would be derivative of NV with respect to N2 at PT and N1. This is called as V2 bar, or partial molar volume for water. So in fact, not just these quantities, I can define other thermodynamic quantities also. I can define H1 bar. It would be derivative of the total enthalpy over N1 when I hold temperature, pressure, and N2 constant. Similarly, H2 bar is going to be derivative of the total enthalpy of the mixture over N2 when I hold temperature, pressure, and N1 constant, etc. I can define U1 bar, which is the H1 bar, remember, is the partial molar enthalpy. U1 bar is partial molar internal energy, right? And again, this is equal to derivative of the total internal energy over N1 at P, T, and N2. Similarly, I can define U2 bar, partial molar internal energy for, let's call it as 1. I can define it for 2. I can define partial molar Gibbs free energy G1 bar, G2 bar, etc. In fact, any partial molar property M can be defined in this fashion. It's the total property over N1, P, T, and N2. This will be M1 bar in a binary mixture, of course. I can extend this discussion to a multi-component mixture when there is more than 2 components, and in that case, we call this as Mi bar. This is the partial molar property for I, and this will be the derivative of the total property over Ni. Because I need Mi bar, I would need to take the derivative with respect to Ni, and I need to hold the number of moles for all the other species J. It can be, if I need it for 1, then I need to hold 2 and all the other species 3, 4, etc. constant. So we represent it as Nj not equal to I. So it would be the derivative of the total property M with respect to Ni when the temperature, pressure, and Nj, where that J is not equal to I, all those moles for all the other species J which are not I need to be held constant. When we do that, we get what is known as Mi bar. This is this expression for a multi-component mixture. So we can extend this discussion from binary mixture to multi-component mixture in a straightforward fashion. So the partial molar volumes, partial molar enthalpies, partial molar Gibbs free energies, etc., can be defined in this way for a multi-component mixture. Now, let's try to write some fundamental property relations for a mixture of chemical species. Now, recall that the Gibbs free energy, the total Gibbs free energy is NVdP minus NSdT. This is applicable for a closed system, single phase. Right? If we have a single phase, homogeneous single phase system, and it is closed, then this particular expression is applicable, is what we said. Now, if we have a single phase system and the system itself is closed, then the number of moles for all the chemical species are same, right? They are not changing. So this expression just considers the change either in the temperature or pressure of the system, but not in the number of moles of the system, because there is only one phase and it is closed. The moles, whatever are present in that vessel, are always present, right? I have a vessel like this, closed vessel. I have something inside this vessel. All that is changing is either temperature or pressure. The number of moles cannot change once it is closed and it is in a single phase. So this equation in that sense is actually applicable not just for a closed single phase system, but it is applicable when we say closed single phase system, it will also be applicable for a system where where the composition is constant. So this system actually, or this particular equation actually, is also applicable for a system with constant composition. I can have a mixture inside this, but as long as it is closed and it is in a single phase, even that mixture can be, or the change in Gibbs free energy of that mixture can be expressed by this particular expression, because the mixture is at a constant composition. Now, what happens if it is not a closed system, if it is an open system and the system is allowed to exchange matter with the surroundings? I can add some number of moles for one of the chemical species or for both the chemical species. It's a mixture of chemical species. Then how do we express the change in Gibbs free energy for such a system? So to answer that question, let us revisit the phase rule. The phase rule says the number of degrees of freedom F is the number of chemical components minus the number of phases plus 2, right? Now, if I have a single phase system with two chemical species, then the number of degrees of freedom is going to be 3, right? So I need to fix 3 intensive variables to completely fix the state of system at equilibrium, right? This is for 2 components and single phase. I have a mixture of 2 components. So we can think of this as the Gibbs free energy. It can be any thermodynamic variable. Let's say it is the Gibbs free energy is a function of temperature, pressure. We need 3 variables. One is temperature, the second one is pressure, and the third one can be mole fraction of one of the components, right? Note that when I say mole fraction of one of the components, I can choose either x1 or x2. Once I choose x1, since the 2 mole fractions should add to 1, x2 is automatically fixed. So I could have said Tp x1, or I could have said Tp and x2. It doesn't matter. I can choose any one of the 2 mole fractions. They are equivalent. So the Gibbs free energy, or in fact any thermodynamic property, is a function of 3 variables. In this case, we chose it to be Tp and x1. Now, if I have a mixture of 3 components and one phase. I'm still talking about a single phase system, but then I have 3 components, then F is obviously going to be 4, as you can see. And the Gibbs free energy is going to be a function of 4 variables. That would be the temperature, pressure, x1, and let's say x2. The mole fractions of 2 of the components. The third component obviously is fixed because x1 plus x2 plus x3 is 1. The mole fraction of the third component is going to be fixed. I can choose any 2 of these 3 variables, x1, x2, and x3. In this case, we are writing it as a function of x1 and x2. So similarly, we can keep extending this. So in general, Gibbs free energy in a multi-component system is going to be a function of Tp, x1, x2, all the way through xm minus 1 if there are m components. Then I need m minus 1 mole fractions and temperature and pressure. So that would be a total of m plus 1 variables. So to fix the state of the system, I need m plus 1 variables, and this is how I can write the functionality for Gibbs free energy. Now let's carry that a little forward. That's the Gibbs free energy, G, which is a molar value, and it is a function of m plus 1 variables, and we are conveniently writing it as G equal to a functionality expressed in terms of Tp, x1, x2, so on all the way through xm minus 1. Now if I ask a question, what is the functionality for the total Gibbs free energy, not the molar Gibbs free energy? Molar Gibbs free energy is an intensive property. The units are something like joules per mole. What I want is the total Gibbs free energy, J. Well, obviously, the total Gibbs free energy is an extensive property. It depends on the size of the system. Do I have 5 moles? Do I have 10 moles in the system? That's going to determine the total Gibbs free energy. So the size of the system matters. So then it's going to be a function of Ng. That's the total Gibbs free energy, right? So let's write it as G total is Ng. It's going to be a functionality expressed in terms of temperature, pressure, x1, x2, all the way through xm minus 1 and n, the total size of the system, n number of moles. Or equivalently, once I have n and x1, n times x1 is obviously the number of moles for 1, n times x2 is obviously the number of moles for 2, and so on. This functionality can be equivalently expressed as it's a function of T, P, N1, N2, N3, so on, Nm minus 1. And the last value I can either write as N, or I can write the number of moles for the last component as Nm. Both of them are equivalent functionalities, right? So then the total Gibbs free energy, Ng, is a function of these variables: m moles, temperature, and pressure. Now if I want to take the derivative, total derivative of this total Gibbs free energy, dNg is going to be the derivative of G or Ng, right? Both of them are same, with respect to the pressure when you hold the temperature and all the moles constant, times dP, plus the derivative of the total Gibbs free energy with respect to the temperature when you hold pressure N1, N2, N3, Nm constant times dt, plus the derivative of Ng with respect to N1, right? When I hold the temperature, pressure, and all the remaining moles except 1. Because I'm taking the derivative with respect to 1, I have to hold all the remaining moles constant. In this case, they turn out to be N2, N3, N4, so on, Nm, dN1, plus the derivative of Ng with respect to now first component 2, N2, when I hold temperature, pressure, N1, N3, all the way through Nm, except everything except N2, times dN2, plus so on, And the last one would be derivative of Ng with respect to Nm when I hold temperature, pressure, N1, N2, and M minus 1 d Nm. This would be the total derivative dNg. Now here I am allowing N1, N2, N3, etc. to change, which means the system can exchange the number of moles of any of those chemical species with the surroundings, so it would be an open system. So this would be the total change in the total Gibbs free energy of the system of an open system actually, right? Now, let's write it here. When I have N1, N2, N3, I'm looking at the first term. When I have all of these constant, all the number of moles constants, then it is as good as a closed system because I'm not exchanging moles with the surroundings. So it's as good as a closed system. And for a closed system, derivative of Ng, just for this particular term, that derivative is Nv. If you recall, it is Nv, right? We said this is for a closed system. So if I write the derivative of Ng with respect to P at constant temperature, then it would be Nv, right? This is true for a closed system. Similarly, derivative of Ng with respect to T at constant pressure is going to be minus Ns, right? This is true for a closed system with constant composition. So I can substitute derivative of Ng with respect to P at constant temperature with Nv, when of course all the other moles are constant, in which case it turns out to be a closed system of constant composition. And again, even for the second term, all the moles from N1 through Nm are constant. So it again is a closed system at constant composition. So this derivative term here would be minus Ns, right? And if you recall the definition of partial molar property, derivative of Ng with respect to N1, when you hold temperature, pressure, and moles of all the other chemical components constant except N1, then this term is what we call as partial molar property. In this case, it is partial molar Gibbs free energy G1 bar. Similarly, this one would be partial molar Gibbs free energy Gm bar, etc. So now I'm going to make these substitutions so that the derivatives look a little simpler, and I'll rewrite this equation. dNg is going to be equal to Nv dP minus Ns dt plus G1 bar dN1 plus G2 bar dN2 plus all the way through Gm bar dNm, right? And partial molar Gibbs free energy is a quantity that appears so often in chemical engineering thermodynamics. We will give it a special name. We're going to call this partial molar Gibbs free energy as chemical potential. It is a very important thermodynamics for separation processes, for chemical reactions, etc. So we give it a special name. We will call it as chemical potential and denote it by a Greek letter mu, and because it is for 1, we'll call it as mu1. The over bar is not required. It automatically mu1 itself is partial molar Gibbs free energy or chemical potential. Similarly, this is mu2, this is mu-m, etc. So if I were to write this expression in terms of chemical potentials, it would be dNg is going to be equal to Nv dP minus Ns dt plus summation over all the species I going from 1 through m, mu I, the chemical potential of that particular species I, dNi. So this is a fundamental property relation for the total Gibbs free energy of the system, of an open system, right? If the system is closed, of course, if you look at this equation, if the system is closed, then dNi for all I is 0, right? Because it is closed, the number of moles for all the species are constant, dNi would be 0. The last term drops out, and this equation reduces to, this is for a closed system, right? For a closed system, dNi is 0 for all I, and this equation would reduce to d of Ng is Nv dp minus Ns dt, which is what we already know, right? So it will go back to its form for the closed system. So this equation in that sense is more general. It is applicable for both open and closed systems. For a closed system, the last term is going to be 0, of course, right? This is called as the fundamental property relation. And in fact, we can write all the derivatives we talked so far by looking at this fundamental property relation. If I were to take the derivative of Ng with respect to P holding the temperature and all Ni is constant, then holding temperature and all Ni is constant will cancel out the second and the third terms. All I have left is the first term, so this will be Nv. Similarly, I can look at this equation and easily write that the derivative of Ng with respect to temperature, holding pressure constant will cancel out the first term, holding Ni constant will cancel out everything in the third term, so this will be equal to negative Ns. Similarly, derivative of Ng with respect to Ni, and remember when I say Ni, this is a summation over a number of chemical components. When I say I, it is only one chemical component, so I need to hold Pt and Nj not equal to I. All other components which are not I need to be held, or the moles for all those components need to be held constant. This would be equal to mu I, which of course is what we know, the definition for partial molar Gibbs free energy, Gi bar, etc. So from now on, when we write these derivatives for partial molar properties, when I say mu I, we're going to ignore this particular expression, right? We'll simply call it as Nj, and by Nj, we automatically mean that Nj not equal to I. So that will make the notation a little easier. So the partial molar Gibbs free energy then is same as the chemical potential, which is the derivative of total Gibbs free energy with respect to Ni at Pt and Nj, right? So now, having said that, let's look at the importance of chemical potential for phase equilibrium, and then certain relationships between various partial molar properties, right? Let's first look at the phase equilibrium part. Now, let's talk about a system that is closed. It has two phases. Any two phases, it can be a vapor and a liquid phase. So let's talk a vapor liquid equilibrium, but then this is extendable to any equilibrium. So I have some liquid mixture here and a corresponding vapor mixture above the liquid mixture. For generality, let's call this as the alpha phase and this as the beta phase. Let's give it a different color. So we have alpha phase on the top and beta phase on the bottom. Now for this particular scenario, let's write the expression for the total Gibbs free energy change of the alpha phase and the total Gibbs free energy of the beta phase. For the alpha phase, dNg for alpha is going to be equal to Nv alpha dp minus Ns alpha dt plus sigma over I mu I alpha dNi alpha. This is the expression for the total Gibbs free energy of the alpha phase, right? Now, let us say that these two phases are in equilibrium, right? And when we have this two-phase mixture, they are free to exchange. The total vessel is closed, but a particular phase is open because it is free to exchange matter with the other phase. So, for example, some moles from the alpha phase can be transferred to beta phase for a component I. Some moles for beta phase can go to alpha phase. So, each phase in itself is an open system, but both phases put together are inside the closed vessel and they constitute a closed system, right? And what we have written here is the total Gibbs free energy for the alpha phase. I can also write the total Gibbs free energy for the beta phase. dNg beta is going to be equal to Nv beta dP minus Ns beta dt plus sigma over I mu I beta dNi beta. Right. Now, notice that we have not used a subscript for P and for T. So, the implicit assumption in here is that they are inside the container, both of them are in equilibrium, so the temperature and pressure for both the phases is same. So, we are simply going to use P instead of P alpha or P beta, T instead of T alpha or T beta. So, these are the expressions for alpha and beta phases. Now, for the total closed vessel, for both the phases put together, right, the Gibbs free energy dNg is going to be the summation of the Gibbs free energies of the alpha phase and the beta phase, right? And it's going to be Nv alpha phase plus Nv beta phase dP minus Ns for the alpha phase, right, Ns for the beta phase dt plus mu I for the alpha phase dNi alpha plus mu I for the beta phase dNi beta, and summation of this over all the components I. When I say all the components I, it is from I equal to 1 to m, where m is the number of components in this particular system. So, this is the expression for d of Ng. The system itself is closed, right? So, because the system is closed, the total volume of the system is not going to change. Now, the system itself is closed, right? When I look at the first term in this particular scenario, Nv of alpha phase plus Nv of beta phase is the total volume of the alpha phase plus total volume of the beta phase. When we add these two volumes, what we get is the volume of the system. We can simply call it as Nv, right? So, d of Ng is going to be equal to Nv, where Nv is the total volume of the system, that for the alpha phase plus that for the beta phase, dP minus S for the alpha phase plus S for the beta phase is the total entropy Ns dt plus sigma over I, this term stays as such, dNi alpha plus mu I beta dNi beta, right? Now, because the system is closed, right, d of Ng is for a constant composition system. When we put both the phases together, this equation should hold. So, this was the first equation and this is the second equation. This is true for any closed system. Once the system is closed, both the phases put together are closed. They are not exchanging matter outside the yellow box. So, the second equation has to hold. Now, from equations 1 and 2, it is obvious that sigma over I mu I dNi for the alpha phase plus mu I dNi for the beta phase should equal 0. Now, if you think about it, dNi alpha is the number of change in I for alpha phase, which means the number, how many moles have changed from the alpha phase. And because Ni alpha, this automatically means that dNi alpha plus dNi beta equals 0. So the number of moles that have disappeared from one phase have to appear in the other phase, or in other words, dNi alpha is negative of dNi beta. So if I take that, then this equation reduces to mu I alpha minus mu I beta dNi alpha is equal to 0, right? So let me extend that a little bit. This would be mu I alpha minus mu I beta, or mu 1 alpha plus mu 1 beta times dN1 alpha plus mu 2 alpha minus mu 2 beta times dN2 beta plus so on all the way through the mth component, mu m alpha minus mu m beta times dNm beta. This needs to be equal to 0. Now, each of these components, N1 alpha, N2 alpha, etc., are independent and arbitrary. We can choose the number of moles for any of the species arbitrarily, and they are independent of each other. And because of that reason, the only way this expression is going to go to 0 is if each of the terms goes to 0, or in other words, mu 1 alpha has to be equal to mu 1 beta, mu 2 alpha has to be equal to mu 2 beta, and so on, all the way through the mth component. Mu m alpha has to be equal to mu m beta. So in that sense, if the phases are in equilibrium, then it turns out that the chemical potential for each of the species 1, 2, 3, all the way through m have to be equal in both the phases, alpha and beta. In addition, of course, we already considered that the temperature and pressure in both the phases are same. So the criteria for equilibrium then is that the temperature, pressure, and the chemical potential mu I for all species I is or are same in both the phases, right? This is the criteria for equilibrium, and now we see why this is such an important variable for chemical engineering applications, right? Chemical potential turns out to be an important variable which decides on how much phase or mass transfer we can achieve from one phase to another. We'll come back to that discussion later on, but for now let's move on with the partial molar properties. So we looked at what partial molar volume is in detail, and then we extended that discussion to various partial molar properties such as Gibbs free energy, enthalpy, internal energy, etc. And it turns out there is a common thread that binds all these partial molar properties. If you recall the discussion we had for the total Gibbs free energy, we can write a similar expression for any total thermodynamic property d of Nm. It would be the partial derivative of m with respect to the pressure when we hold temperature and Ni constant times dP, the partial derivative of m with respect to the temperature when I hold pressure and Ni constant times dt, plus the partial derivative or summation of the partial derivatives of Nm with respect to Ni when I hold Pt and Nj constant, right, dNi. And the last term is what we called as the partial molar property Mi bar. So I'm going to replace the last term with Mi bar just to make it simpler to handle. It is Mi bar dNi. Now d of Nm is m times dn plus n times dm. And similarly, if I write Ni is the total number of moles multiplied with the mole fraction, then dNi is going to be d of n times xi, or n times dxi plus xi times dn. Now let me put these two expansions in the previous equation so that what we get is n times dm plus m times dn is the derivative of Nm with respect to P, temperature Ni dP, plus derivative Nm T, pressure Ni dt, plus Mi bar N dxi plus xi dn, right? So we'll take this equation here and try to rearrange the terms a little bit. What we get is dm minus the derivative of nm with respect to p at t and ni, right? And when I hold all the ni, okay, let's make one other. Now the derivative of nm with respect to p, when I hold all the ni's constant, it automatically means the total number of moles n is constant. So this can come out of this derivative. So this will be n times the derivative of m with respect to p, and because all n's are constant, I can also claim that the mole fraction x is constant. Similarly, for the second term, derivative of nm over t at p and ni will be n times derivative of m with respect to t at p and x. So I'm going to make, let's number them so that it's easy. This is 1, 2, 3, 4, 5, and 6. So what I'll do is I will substitute 2, 3, 5, and 6 in 4. I'll make this substitution, do a little bit of rearrangement of the terms, etc. And if you do that, I'll leave it for you to do it. If you do that, what we will end up with is dm minus derivative of m with respect to p tx dp minus derivative of m with respect to t px dt minus sigma over I mi bar dxi multiplied with n plus m minus sigma over I xi dmi bar multiplied with dni or dn equals 0. So we rearranged the terms and made those substitutions to get this equation. And once we are at this stage, if you look at it, what this tells me is that sum of two terms needs to be 0. And if you look at this equation, there are two terms in this equation. The first term is multiplied with n, the size of the system, and the second term is multiplied with dn, or the change in size of the system. Both these quantities, n and dn, are arbitrary. I can choose any size of the system, and I can decide to change that size by any amount I wish to, dn, and both of them are independent and arbitrary in that sense. And the only way this particular equation will be applicable then for all the scenarios is if each of the terms inside the parentheses is going to go to 0. And if that happens, the first term is an equation which we already know. The total molar property m is going to be the derivatives of the partial properties dx dp, is going to be the total molar property m is going to be the derivative of m with respect to p at t and constant t and x dp, derivative of m with respect to t at constant p and x dt, plus sigma mi bar dxi over all I. The second equation is m is sigma xi mi bar, again over all I. Now this first equation here is actually a special case of the equation we already know, right? If you take this equation 1 and you make the total size of the system n equal to 1, right? In equation 1 here, if I put n equal to 1, what we get is dm on the left hand side, dm over dp, dou m over dou p at constant t and ni. If all ni's are constant, it automatically means the mole fraction of all i's also is constant, right? So it is same as dou m by dou p at t and x dp, dou m by dou t at p and x dt, plus sigma mi bar, and when the size of the system is 1, dni equals dxi if the total number of moles is 1, right? So the last term will be dxi. So this equation 1 essentially reduces to what we have here. This is a special case of 1 when the size of the system is 1, right? And the second equation, however, is an outcome of this whole exercise. It says that the total molar property m is equal to summation of the partial molar properties weighted with the respective mole fractions xm, m bar. So you weight all the partial molar properties with their respective mole fractions, add them, that will give the total molar property for the mixture. This is an important outcome. So when we mix components, the partial molar, the volumes are not additive, right? But then what are additive is the partial molar volumes. If we know the partial molar volume, then we can say that the total volume for the molar volume for the mixture is going to be x1 v1 bar plus x2 v2 bar. For a special case, v1 bar might be same as v1, v2 bar might be same as v2, etc. But irrespective of whether it is true or not, this particular expression is always true for a binary mixture. Not just volume, for any molar property m, not just for binary mixture but for even multi-component mixtures, m will always be equal to sigma xi mi bar. And we call this relation as summability. We're summing the partial molar properties with respective or weighted with their respective mole fractions, and we call this as summability relation. So that's the take-home message for today's lecture. We'll hold on to that, and when we come back in the next class, we'll talk more about solution thermodynamics. Thank you.